Okay, so hello everyone, we are live. Welcome to the ETH Research Grant Round 5 applicant demo. Just to give you guys a brief overview of what the ETH Research Grant is, it's funded by Dora Dōjo, and we commit to finance the projects and the research initiative within the Ethereum ecosystem. And yeah, it's a long-term grant program. We accept the projects on a rolling basis as and when you submit your project. Today with us, we have Conway from OPML. So OPML is a solution which supports machine learning on the blockchain. Definitely Conway would be the right person to talk more about that. If any one of you watching us today has any question, feedback, etc., about the project or anything you want to ask from Conway, please feel free to put down your question in the comment section and we'll pick it up towards the end. Welcome, Conway. Any opening thoughts that you'd like to share? How was the building journey? What was the entire process like, and so on?
Yes, and so the introductions, and I will share my screen first.
Perfect.
Wait a moment. So, can you see my screen now?
Yes, I can see it now.
Oh, yeah. And thanks for the introduction again. And I'm Conway. And today, I'm going to talk about our project, OPML, the Optimistic Machine Learning on Blockchain. So, at the beginning, I will first introduce the diagram of the proof system. On the current blockchain system, there are two kinds of popular proof systems. One is used ZK proof, another is flop proof. And the current rollup system with ZK proof is known as ZK rollup. And the rollup system with the flop proof system is known as optimistic rollup, also known as OP rollup, such as optimism and arbitrum. However, for the on-chain AI or on-chain machine learning, most of people are focused on the ZKML, and I think many people have heard about the ZKML. ZKML is indeed a on-chain machine learning using the ZK proof. So we're wondering that whether it is possible to enable on-chain machine learning using the flop proof system. And based on this idea, we propose OPML, the optimistic machine learning on blockchain using the flop proof system. So compared with OPML and ZKML, we can find that the ZKML has its own limitation. In ZKML, we need to generate a zero knowledge proof for the inference of machine learning, and the cost of generating a zero knowledge proof is extremely high. Therefore, ZKML can only support some small model on the blockchain, and which limited the application of ZKML. And our proposed OPML uses a flop proof system, and the cost of computing a flop proof in OPML is extremely cheap compared to ZKML. Therefore, the OPML can support extremely large models such as Stable Diffusion and some large language models such as Llama. And this large model this large model cannot be handled in the ZKML, but it is possible and practical in OPML. So, how OPML works? The OPML process goes as follows. The requesters will first initiate a machine learning inference task on chain, and then the servers will finish the machine learning task and then commit a result on chain. Optimistically, we assume that the committed result is correct. But the problem is that what if the committed result is incorrect or something wrong? Indeed, there exists a challenge period in OPML to avoid this. During the challenge period, anyone can challenge the results by computing a flop proof. And if the flop proof succeeds, the OPML protocol will update the result and will punish the server who provide a wrong result. And if the result remains unchallenged after the challenge period, the provided result will be valid and accepted. Indeed, the whole process of OPML is quite similar to the whole process of optimistic rollup. But there's a key challenge in OPML. This is how to enable the machine learning computation in the fraud systems. As we know that currently, most of the machine learning computation is handling in the popular machine learning frameworks such as TensorFlow, Python, and on some high-performance device such as GPU and multi-thread CPU. But how to make it in the fraud system? And faced with this challenge, in OPML, we first built a fraud-proof virtual machine for off-chain machine learning execution and on-chain arbitration. And because of the current popular machine learning framework such as Python and TensorFlow is heavy and heavy and not suitable for the fraud system, we implement a lightweight framework for the machine learning, and we also provide a converter that can convert the Python model or TensorFlow model to OPML model. Therefore, you can train your model using Python or TensorFlow, and then use our converter to convert to OPML model. And the most important thing is that we use a cross-compilation technique that can compile the AI model inference code to the virtual machine instruction. In that way, we can convert the whole machine learning computation to the virtual machine program instruction. Therefore, we can doing the fraud proof using the virtual machine. And the virtual machine image is managed by a Merkle tree, and we only store the Merkle tree root on chain. Therefore, the on-chain storage cost is very low. So how to submit a fraud proof in OPML? Indeed, during the challenge period, if someone thinks that the submitters submit a wrong answer, then you can challenge the submitters, and we can call this service as a challenger. And if the challenger wants to challenge the submitters, which means that the challengers and submitters have a different state. Recall that we have just converted the whole machine learning computation into the virtual machine instructions. Suppose that a machine learning inference can be compiled to 100 virtual machine instructions, and this instruction is very basic, and each instruction is such as like adding the value in the register in the virtual machine or accept the memory in the virtual machine. And the virtual machine will execute this instruction one by one. And after executing one instruction, the virtual machine state will change from one state to another state, such as, for example, the virtual machines, the register may change, the PC in the virtual machine may change, and the memory in the virtual machine may change. Therefore, doing the machine learning computation in the virtual machine will leading to the virtual machine state change from the initial state S0 to S1 to S2 and to the final state S100. And the challenger thinks that the submitted result is incorrect, which means that the challenger and the submitters disagree with the final virtual machine state, which means that the S prime 100 is not equal to S100. And then in this way, the challenger will start a bisection protocol with the submitter to find a dispute point. The challenger and the submitter will first check the middle point, that is the middle state S50. And if the submitters and the challenger agree with the middle state which means that the state 50 equal to state prime 50, which means that the first 50 instruction work correctly, and the dispute point lays in the last 50 instruction. And then the bisection protocol will continue. And this time, the submitter and the challenger will still check the middle point, that is state 75. And if at this time the submitter state S75 is not equal to S prime 75, which means that the dispute point is placed in the state 50 to state 75. And the bisession protocol will continue. And at the next state, as the next round, the challenger and submitter will also check the middle point, the state 63, and the bisession protocol will continue. And finally, the submitter and the challenger will end at the final state, where the submitter and the challenger will agree with the state Si, but disagree with the next state Si plus 1, which means that Si is equal to S prime I, but Si plus 1 is not equal to S prime I plus 1. At this time, the submitters and the challenger will send the state Si to the on-chain virtual machine, and the on-chain virtual machine will execute one instruction and will calculate the correct next state S prime. If the next state is S prime I plus 1, which means that the submitters calculated a wrong result, and the submitter will be punished, and the challenger will update the result of the machine learning.
Hey,
But
Conway, I just
yeah,
wanted to ask if you're changing slides because we can still see the slide one. So if you're changing slides, we're not able to see the further slides.
so you don't see the slide change.
No, we only see the slide one.
Oh, sorry, there's something wrong. I'll share the screen again.
Yes, please.
So can you see my screen now?
No, not yet. Yes, now we can see the proof system slide.
And the next slide.
Yep, is OPML versus EKML.
Okay, I'm sorry for
Perfect.
that.
No problem.
So should I go through the previous slides?
Maybe go through the infra and the mechanism once again.
Oh, okay.
Yeah.
So sorry for that. I will introduce the proof system again. And as mentioning about during the challenge period, anyone can challenge the submitter. And suppose that there is a challenger who are going to challenge the submitters because he thinks that the submitter submit a wrong result. And since that we have converted the machine learning inference process into a virtual machine code. Therefore, we can just challenge on the virtual machine. And since the challenger disagree with the submitters, which means that the final state of the virtual machine are different. That is, S prime 100 is not equal to S 100. And then the challenger and the submitter will start a bisession process. The challenger will first check the middle point, that is the state 50, with the submitter. And suppose that at this time the state 50 is equal to state prime 50, which means that the first 50 instruction was correctly, and the dispute point will list in the next 50 instructions. And the bisession protocol continues, and the challenger and the submitter will still check the middle point, the state 75, and suppose at this time the state 75 is not equal, and which means that the dispute point should lay in the state 50 to state 75. And the bisession protocol will continue, and finally, the challenger and the submitter will reach the final state, where the challenger and the submitter will agree with the state Si, but disagree with the next state. In this time, the challenger and the submitter will submit this state onto the on-chain virtual machine, and the on-chain virtual machine will execute one instruction and calculate the next state of the virtual machine. And suppose that the next state is S prime I plus 1, which means that the submitter is wrong and the challenger is correct. And in this time, the submitter will be punished and the challenger will update the machine learning results. However, the current throughput system has its own limitation. The current throughput system can only handle the single-thread execution in a virtual machine and cannot use the GPU, TPU, or multi-thread to speed up. To handle this problem, we first propose a novel multi-phase verification game. In this verification game, the submitters and the verifier will place a multi-phase. For example, they will first find a verification game of the computational graph and find a dispute node and then continue to do that. And the multi-phase verification game can help to shorten the execution in the virtual machine. Another problem is about the consistencies. And as we know that the native execution of DNN computation cannot guarantee the consistencies. This is because that the parallel computation involving floating point number will often provide non-identical outputs due to the rounding errors. Besides, the hardware platform of operating system can also affect the computing result of the floating point. However, the consistency is very important in OPML because without this consistency, the throughput system cannot work, and we cannot replay the results. So, to guarantee the consistencies of OPML, we adopt two technologies. The first one is using a fixed point, the quantization technique. The next one is that we introduce the software-based floating point libraries to guarantee the consistencies of the calculation of floating point. And now we are going to compare the OPML and ZKML. And for the proving systems, the ZKML adopt the zero-knowledge proof, but OPML adopt the throughput system. And since the cost of generating a zero-knowledge proof is very high, therefore the ZKML can only support very small or limited AI model. But for OPML, since the computing the throughput is very cheap, therefore OPML can support any size of model. And indeed, OPML is available for extremely large model. And as for the device requirement, ZKML requires the device have a large memory because generating a ZK proof requires a large memory for ZK circuits. However, OPML can calculate the throughput systems in native environment. Therefore, OPML can conduct it in any PC with CPU or GPU. And as for the service cost, the ZKML has a very high service cost because the cost of generating a zero-knowledge proof is much higher. It's very high. Indeed, the cost of generating a zero-knowledge proof may be tens of thousands of the calculation in the native environment. And for OPML, since OPML can be conducted in the native environment, the service cost for OPML is very low. But OPML has its drawback, and indeed, this is a drawback for all the throughput systems. The OPML needs to delay for the change period, and however for ZKML can achieve instant finality, and there's no delays for ZKML. But we also need to wait for the proof of generation time, and for some large models, generating a zero-knowledge proof for some large model may cost several hours. And as for the security model, since the ZKML adopts the zero-knowledge proof, therefore, ZKML can achieve the cryptographic security, which is the highest level of security. But for OPML, OPML needs the challenger to verify this result. Therefore, OPML is crypto-economic incentive security. Indeed, the comparison between OPML and ZKML is quite similar to the comparison between OP-rollup and ZK-rollup. And we want to highlight that OPML can provide machine learning service with low cost and high efficiencies compared to ZKML. And the requirement for OPML is extremely low. And we now are able to run OPML with large language model. That is, we run a 7 billion llama on a common PC even without GPU. And this code running llama is open source. And as for the future work, One approach is that we want to optimize the proof persistence, and specifically, we want to shorten the challenge period. We know that a challenge period is related to the execution time and the number of interactions. And to shorten the execution time in the virtual machine, we propose a multi-phase verification gain. And to reduce the number of challenge response interactions, we plan to adopt the multi-step ZK throughput and the multi-step challenge points to reduce the interaction. With this optimization, it is possible for us to shorten the challenge period for OPML from several days to several hours or even shorter. Another approach is that we are going to investigate the combination of OPML and OP rollup. Indeed, we are planning to develop an optimistic rollup layer 2 chain with OPML as the pre-compiled contract. In that way, it is possible for us to use machine learning inference natively in the smart contract. That is, you can call a machine learning model in a smart contract directly, and we think this can boost the Web3 application. And that's all. Thank you.
Lovely. Thanks a lot, Conway. That was pretty impressive. A great thing that you're building, and thank you for contributing to the Ethereum ecosystem. I'm actually curious to know. We also have a lot of people watching us, by the way, and yeah, seem pretty interesting. And I'm actually curious to know with the OP roll-up ecosystem and the OPML ecosystem, how does it both complement? How does OPML rather complement the OP roll-up ecosystem, and how do they sit in conjunction with each other?
Well, indeed, we can develop a layer 2 chain using OP rollup. And in this layer 2 chain, we can define a pre-compiled contract. And this pre-compiled contract will allow us to do the machine learning inference directly in the smart contract. And for the rollup system, uh, since this layer 2 chain adopt optimistic rollup, and when checking the state in this layer 2 chain, and when, when you when you, when you come to the pre-compiled contract of the machine learning, and we will adopt the OPML to verify this part. And with this, we think that it is possible to use the machine learning directly in a layer 2 chain with optimistic rollup.
Understood, understood. And yeah, another important aspect of this is training language models. So how does OPML support the training?
Yes, indeed. The current project, OPML, is mostly focused on the inference part. And we also investigated the training part. And we think that the training in OPML is possible because in OPML, we just convert all the computation in the machine learning to a virtual machine code. And indeed, the training process is similar. We can convert the training process into a virtual machine code and use the proof system to prove that.
Interesting, pretty interesting. And you also spoke a little about the challenging period. Major goal would be to reduce the challenging period. But let's say about reduction, how much does the challenging period? What does the challenging period comes down to?
Well, indeed, this part is still under development, and currently, for an OPML model, for example, for a 7 billion llama, and this challenge period will last for around for about 20 minutes in the testnet, and therefore, the challenge period for OPML, for example, for a llama may last for 1 day or even longer to guarantee the security. So we're wondering that whether it is possible to shorten this challenge period. For example, we are considering about using some ZK throughput or using some multi-stack challenge point to reduce the interaction time and using the multi-phase to shorten the execution time in the virtual machine.
Understood. Got it. Thanks a lot, Conway. Those were all the questions that I had for now. Definitely pretty interesting. I will dive into this more. And congratulations for being with us here today. I think everyone seeing us live is pretty much on board. But yeah, once again, thank you for taking part in the ETH Research Grant, and thank you for constantly supporting the Ethereum ecosystem and pushing it towards further development.
Thank you.
Thanks a lot, everyone, for watching. And please feel free to head on to the build link. It's on the chat. Read more about what Conway is building with OPML. What does the future roadmap looks like, and dwell more into it. Thanks a lot, everyone. Thanks, Conway. Bye.
Thank you. Bye.